Asteroids are rocky objects that did not accumulate into larger bodies. They're kind of like the leftover material in the solar system that didn't combine to form a planet. They're not the destroyed remains of a former planet, they just never formed anything larger. Some asteroids even have smaller asteroid moons orbiting them. Most asteroids orbit the Sun between the paths of Mars and Jupiter, the main asteroid belts, although some are found in other areas. A Lagrange point is an area of space that is gravitationally stable, where forces are balanced. James Webb orbits the Sun at Earth's second Lagrange point and its halo orbit. Trojan asteroids orbit in Jupiter's Lagrange points, but Jupiter, with its large mass and subsequent gravitational influence, it creates gaps known as Kirkwood gaps in the asteroid belt where asteroids cannot orbit. However, there are some asteroids that do have highly elliptical orbits and pass through the inner solar system. An example of this could be the Apollo asteroids, which cross the Earth's orbit. We visited asteroids for multiple purposes, whether as targeted missions, such as JAXA's Hayabusa probe, or Galileo on its way to Jupiter, passing 951 Gaspra and 243 Ida, which has a small moon named Dactyl. Asteroids can be made of a variety of materials. Of course, there's 16 Psyche, a rich metal asteroid of great material worth by human standards, but actually there are 3 more broad classes. 75% of known asteroids are C-type carbonaceous asteroids, 17% are silicaceous, S-type, and the final 8% are metallic, M-type. But the wide variety of this composition is important to us as scientists. We want to understand our origins within our solar system, and by studying asteroids, we get this key insight about what this solar system looked like 4.5 billion years ago. Asteroids are the fundamental building blocks of the solar system, providing essential insights to understanding not only the system's formation, but the formation of Earth and the foundations of life itself. The asteroid we studied in this project is able to be identified by its number, 14691. It was selected using the Minor Planet Info Observations target search and was selected based on its location, whether it would be near opposition at or near the time of data collection. For reference, when an asteroid is at opposition, it means that the Earth is exactly between it and the Sun. From there, the JPL Small Body Browser allowed the determination of the asteroid's coordinates on nights where time was available.
The main goals of this project were to determine the shape, rotation, composition, and distance of the asteroid. These goals were successfully met using astronomical image processing software and empirical methods of data collection.
The image sequences for this asteroid came from the Southeastern Association for Research in Astronomy, or SARA, and more specifically, the SARA CT and SARA RM telescopes. Just to give a brief background on these instruments, SARA CT is a 0.6 meter telescope located in Chile, and SARA RM is a 1 meter telescope located on the Canary Islands. Our asteroid data was collected during the months of April and May, with each data set recorded within a span of a day. The majority of the images collected from the telescopes were calibrated. This means that frames were used, bias, flats, and dark frames, to remove any noise, vignetting, or dust in the optical setup. To perform the photometry on this data, the software AstroImageJ was used.
Photometry has to do with the measurement of the amount of light within an aperture of a fixed size, measurement of the brightness of stars or other objects, like the asteroid we're studying in this project. It's normally done through the usage of filters, where you're subtracting color and filtering out different wavelengths of light. What we're trying to do is figure out the brightness of the asteroid as it can be seen in the sky, and by using a comparison star of a known fixed magnitude or brightness, we're able to determine that accurately.
After loading in the dataset, we simply located the asteroid and used the comparison star to generate a magnitude for the asteroid. For each dataset, we equally divided the magnitude amongst our team and compiled it into a table, along with the Julian date for each image. To further collect data on the specific shape of the asteroid, we were assigned to create models. Collectively, we decided that potatoes would be a great model, as their varying elongations could help us assess a potential shape for our asteroid. We also modeled styrofoam into different shapes to achieve the same feat. I'm going to hand it over to Pablo to talk a little bit more in depth about our asteroid modeling.
Using layered styrofoam, I was able to cut out and mold an approximate shape of our asteroid. I then painted a wooden stick and created a floating platform for the asteroid model. Using a green screen, I was able to shoot a sequence of 16 images, rotating the asteroid on its 3 axes for a full rotation. From there, I composited the images in Photoshop, removing the green screen and putting a generic starfield image to simulate an asteroid in space. Heading over to Astro Image J, I performed photometric practices that we learned and applied them to this model, which resulted in a light curve depicting my model asteroid over an arbitrary period of amount of time. Here's a GIF of my model asteroid tumbling through space. Our asteroid actually has more of an oblong, elliptical shape, so a potato seemed more like a better option to model. Using a drill, Rajvir attempted to spin his model asteroid. However, we were unable to successfully use a potato for a model. After this, we created a graphical representation of our actual datasets, including the asteroid's real shifting magnitude and variable rotation rates. The first graph depicts the asteroid's magnitude versus Julian day on the night of May 21st this year. Through analyzing trough to trough and peak to peak, we found the rotation rate was 0.50 Julian days, or about 4 hours. On the night of May 17th, we found the asteroid's average rotation rate to be 0.150 Julian days, or just over 3.5 hours. Something to note is the noticeable shift in values near this peak, which was actually due to the asteroid passing over a background star, ultimately shifting its true magnitude. On the night of April the 20th, we found the rotation rate to be 0.15392 Julian days, or just over 3 hours and 40 minutes. With careful analysis, we averaged the rotation rate from May 17th, 3.61, and April the 20th, 3.69. This averaged to a rotation rate of 3.65 hours, which lies in conjunction with the self-reported rotation rate of 3.6524 hours from the asteroid's original discoverers. It was a near-perfect match. Finally, we individually created graphs using color filter data from May 17th, as seen here. The BV color index was plotted against the V magnitude of the asteroid per common practice in observational astronomy.
Our final goal was to understand the distance of the asteroid from Earth. In order to do this, we needed to calculate the parallax near the time of opposition. But what exactly is parallax? Parallax is defined as the apparent displacement of an astronomical object as a result of the change in the observer's point of view. Since we only tracked the asteroid with one telescope, we recorded the displacement of the asteroid over time in the X and Y planes between the 2 images, about 3 hours apart. After converting this displacement to degrees, we further calculated the displacement of the Earth's orbit between the time of the 2 images. Using this information, along with some trigonometry, a distance of 1.57 astronomical units between the Earth and the asteroid was calculated. We found that this value was close to a previously calculated Earth distance value of 1.584 astronomical units.
To calculate the parallax of our asteroid, we actually had to use a different method than what is normally used. This is because one of the telescopes we were supposed to use was in the middle of a blizzard. So this definitely emphasizes some of the challenges that come with ground-based telescopes. So in order to calculate the parallax, we had to use a different method than usual. Normally, parallax is determined using 2 telescopes and the asteroid. However, because we only had access to one telescope, we used said telescope and 2 different locations of the asteroid. As per usual, with many scientific observations, we ran into a few more challenges as well. One of the biggest challenges we encountered was determining the color index of the asteroid. We used 2 color filters, blue and green, to find the asteroid's color at various points in time. By doing this, we hoped to see whether the asteroid changed color. If our graph was unchanging, the asteroid's color would be unchanging as well. If the graph had curves or a nonlinear shape, we would know that the asteroid is changing color. Unfortunately, we ran into a bit of a challenge. For our first run, we divided up image analysis among the members of the team, each person getting about 6 images to analyze and record data for. We then compiled all of our analyses into one graph. However, when this graph was completed, the data points on it were scattered and didn't follow any visible pattern, as you can see here. So we tried a different approach. Instead of dividing the images among team members, each member analyzed the entire data set. Then we each made our own graph. However, this didn't turn out too well either. Each one of our graphs were totally different, and once again, none of them followed any kind of pattern that we were expecting, as you can see. Ultimately, we decided that it was possible that the asteroid was changing color, but there wasn't enough definitive evidence to make any concrete conclusions. In this case, we would need more data in order to be able to make a final accurate interpretation. So as you can see, we definitely encountered a few problems, but as our mentor likes to say, if you don't have to do it 3 or 4 times, you're doing it wrong.
Not inconclusive, it was interesting to see the way the graphs came out, and we had a good time trying to come up with reasons for why the data might have come out this way. But as was previously mentioned, we decided to move on to the next step of our project, which was modeling. A big highlight of our work ran into plenty of problems and had to revise our procedure for making the models many times. First, our plan was to put a potato on a drill and take to find the potato's light curve. But while doing that, we found that the drill spun too quickly and in some cases flung the potato off of it. After attempting it this way, we put the potato into a stand and moved the potato by hand, taking pictures between each movement. Though doing it this way took more time, our team enjoyed the process of working on the models. Another part of our work was the parallax. Instead of doing parallax the traditional way of 2 telescopes in the asteroid, we had 1 telescope with the asteroid in 2 different locations. When we first started working on the parallax, we were confused on how we would do this, but after getting some help from our mentor, we were able to better conceptualize how to do the parallax and get the data. And lastly, here are our individual relationship. I really enjoyed the opportunity to work with our mentor, Mr. Rutherford, throughout this past month, and I'm grateful for all he taught us throughout the program, including using new softwares, analyzing data, and the more conceptual stuff about astronomy. I had a great time working on this project and learning from my peers. This was an amazing internship experience.
I just want to say thank you to everyone who made this internship possible. I had a great time and learned a lot in the process. But I didn't just learn how to find the rotation rate of an asteroid or how to analyze image data using complex software. I learned what it means to be a good teammate. I'm really grateful for everything this program has to offer, and I look forward to using what I've learned in future endeavors.
I'd like to formally thank all institutional entities involved in the SEAS internship, including NASA, the Texas Space Grant Consortium, and the Center for Space Research. With their grants and support, the SEAS internship is able to foster young scientists and lend credibility to the importance of educating America's rising scientists. As an aspiring astrophysicist, this internship has strengthened the resources and skills that I need to successfully pursue this career, from creating a collaborative environment with my peers to independently meeting goals using intricate software. Similarly, this internship has given me the opportunity to be published in my local newspaper and network with regional Nevadan scientists in the Nevada Space Grant Consortium. I am most proud of our wonderful mentor, Mr. Rutherford, who has lent us his valuable time and helped us advance our abilities as rising scientists. I am also thankful for being part of such a vibrant team of people that want to create big changes in this world. With our engaging meetings and fun jokes, we've established a bond that will last past SEAS. Thanks again to everyone for this amazing opportunity. I'm proud of representing my community as a NASA SEAS intern, and I hope one of you watching this can say the same thing next year as well.
This internship was a one-of-a-kind experience where I've grown both as a person and a scientist. Firstly, I want to thank Mr. Rutherford for all he has taught us throughout the internship. We are truly grateful to have had such a knowledgeable and helpful mentor who always encouraged us to be resilient as a part of the scientific process. I also want to thank my fellow photometrists who have made this experience truly memorable. As an aspiring astrophysicist, this program has provided me with excellent research skills and has solidified my passion for exploring the universe. Whether it was creating and analyzing light curves or setting up a potato drill model for our asteroid, I've truly enjoyed my time in the NASA SEAS internship, and I will be sure to carry the lessons I've learned here to my future scientific endeavors.
This program was amazing, not only to have the opportunity to work with peers across the country and an amazing mentor, but also to learn more about Earth and space science, both through our assigned project and through all of the speakers that we learned from throughout the internship program. This is all we have for you today. A big thank you first to our mentor, Tom Rutherford. Without him, this project would not have been possible. Secondly, we'd like to recognize SARA, the Southeastern Association for Research in Astronomy, for telescope access and time to collect data on our asteroid. Our sincerest thank you to the SEAS program for providing us the opportunity to connect with each other and together learn about the fields of Earth and space science and the opportunity to do some real science. And finally, to our audience, thank you so much for being here, and I think it's about time to open it up for any questions.